So I'm going to present a work.
Sorry.
Okay. So I'm Iris Paparelle. I work with Valentina Parigi and Roberta Zambrini in Paris, in Laboratoire Castelem-Cossel, and in IFISC in Mallorca. And I'm going to present you a work that was recently published by our groups that is entitled, that is named Experimental Memory Control in Continuous Variable Optical Quantum Reservoir Computing. So it's a very long title. We're going to break it down step by step, hoping that it will be clear. So the first thing is reservoir computing. So reservoir computing is a subclass of machine learning. In particular, it comes from the field of recurrent neural networks. So we have some inputs that we want to learn a target task on, for example, images, and we want to give the names of the images to the images. And we're going to train a system with some obvious answers to reply to some questions. And then we're going to test it on a test set. Usually this is done using deep neural networks in which we have a lot of neurons that are connected by weights. And we're going to train this whole system with tuning every single of the connection between the neurons. And this tuning is also going to be updated in real time. So it's going to be a very heavy training because a lot of parameters and a lot of work during time. So what is the solution to this heaviness? It is to substitute this whole part with a physical system that we're going to call a reservoir. That is going to be our ready-made computation engine, meaning that we're just going to do the training of this last part, and this is just one layer. It's going to be a linear regression, and it's going to be very fast to do. And we're going to keep the reservoir fixed. It can be analog, quantum, photonic, biological. And it is going to be very fast from a computational point of view. Does it work all the time? Of course not. The reservoir has to have some characteristics in order to work, otherwise it would be too easy. In particular, it has to have fading memory, like a child that learns, it has to forget a bit to learn new things. No linearity, that we've seen in many talks is very important. Separation property, meaning that it can distinguish what you send. Rich dynamics and high dimensionality. Once we have all this, we can do time series forecasting, signal processing, and classification. So in this way, we moved the computational cost and even the energetic cost from the training to the physical substrate, meaning that all the energy is going to be employed to build this physical reservoir. So how does it work? We have an input series that we want to do a task on. We're going to encode it on the reservoir somehow. It's going to evolve. And then we're going to measure a part of it to get some observables. And we're going to build an output by doing a simple sum of these observables. Once we've sent all our training data, we do the linear regression at the very end on the training set, and we're done. So, as I said, minimal training cost, and we don't need to iteratively change the weights, we just do it at the very end. So now we're going to go a bit further in what I actually did. First, I'm going to give you some building blocks to understand the experiment. Then I'm going to show you the experiment. And in the end, the results. So let's start from very far. Light is a wave. So it has an amplitude and a phase. And when we actually look very closely, like quantum scientists, we see that there is some noise, meaning that even if we observe vacuum, there will be always some uncertainty that respects the Heisenberg principle. All this we can represent very easily in a phase space, where we have an angle that is the phase and an amplitude, and the noise is just some sphere around our state. Sometimes, though, we can have squeezing, meaning that we reduce the uncertainty below the vacuum level in one of the two axes. And this will be very useful for later because it's really a resource. All of this is continuous quantities, so at least now we understood why I was talking about continuous variables. How do we get squeezing? With parametric down conversion, which is a nonlinear process. You have a nonlinear material, like a crystal or a waveguide. You pump it very strongly, and the light that you have at the output will be squeezed if your material has some specific characteristics. And this is a deterministic process, meaning that when you have your waveguide, you align it, you send a pump light, you have your squeeze light at the output. To make it a bit more interesting, we're going to use pulse light, meaning that we can do temporal and spectral multiplexing, because since we use very short pulses, we have a very big spectrum. And not only we can work on the frequency bands, but we can even work on another basis, like the Hermite-Gauss basis. Why am I talking about specifically this basis? Well, because if you send a Gaussian pulse into our nonlinear material, you're going to have light that is squeezed only in this very specific basis, meaning that the squeezing appears when you measure in this basis. So in this way, we can use, we can have multiplexing, because we have a lot of frequency bands, and high bandwidth. What are we actually measuring? So we're using what Johan talked about yesterday, the homodyne, which is a projective measurement in the phase space, and which is room temperature, good power consumption, and can be easily integrated. And basically, you make your signal interfere with a local oscillator, very strong coherent laser, that you can also shape. And by shaping the spectrum of the local oscillator, you decide what basis you are measuring. Everything is Gaussian until now, meaning that we can just use mean and covariance to describe our states. And if we are in vacuum, only the covariance. This is the covariance matrix, the expression. And each small 1 or 0 is the mode that I'm measuring. And if I measure in the right modes, well, my covariance matrix is just a diagonal. Squeezed, anti-squeezed, squeezed, anti-squeezed. What happens if I measure in another mode, in another basis than the squeezed basis? I basically just do a change of basis. So I go from a diagonal to a off-diagonal, a non-diagonal covariance matrix, meaning that now with these new modes, I have correlations, so entanglement, between them. And this measurement basis change is a passive operation, so it's not so difficult to do. It doesn't require a lot of energy. Are we fulfilling the requirements of reservoir computing? So what I will do is to encode information on the phase profile of the pump of my nonlinear process. And then I will measure the covariance matrix, because it's what I can do, in an interesting frequency mode basis, so that I can have the entanglement and the correlations. In this way, I will have separation property, because my crystal sees when something changes, luckily. I will have high dimensionality, because I can measure a lot of modes, and it scales up quadratically. I can have nonlinearity, because changing the phase, at least I have cosinus and sinus. Rich dynamics, and okay, the fading memory is missing, but I am tweaking it in by putting an electronic feedback, meaning that yes, I'm sending a lot of pulses and forgetting about them, but what I measure, I re-encode when I encode the input. So just to have a recap about the energy, so minimal training cost and no iterative optimization, thank God. And then, since I'm working with photonics, I can have passive linear optics, multiplexing using a lot of frequency bands, high bandwidth, work at room temperature operation, and produce my states deterministically. Also, spoiler for the end, since we're quantum, I will have a polynomial scaling of the performance of the reservoir. So let's go to the experimental platform now. So this is what we did on the experiment. So we have our laser that then we divide in two. One part would be the LO, so the thing that we use to select which modes we are measuring, that will be shaped. And then we have the pump that will be rotated by an electro-optical modulator. So basically, to this electro-optical modulator, I'm sending a voltage that will be proportional to the input that I want to learn, SK. And then it will evolve through my crystal, through my measurement process that is interesting enough. And then I will get some observables that are the elements of the covariance matrix. And these observables, I will feed them back into the input encoding. So in this way, I also have the fading memory. Another thing that we could do, but we didn't until now in the experiment, is to actually exploit the fact that we have a broadband thing and do some pump spectral shaping as well. So just to recap, we have our squeeze modes out of our crystal. We measure them interestingly enough, so we have correlations. And if we change the original pump, well, the system will change again. So we will have a lot of diversity that we can exploit to do our reservoir computing. So now come the part of the results. So this is what we did on the experiment, the global phase encoding, meaning that we just turn the whole pump. So by turning just the whole pump, you can measure all just one mode, the quadratures and the correlations. And you can see that we have a sort of cosinus or sinus behavior, which is nonlinear enough to do what we want to do. And of course, okay, we also have some noise when we don't do a lot of averages, but we can simulate pretty well what is happening. So the first task that we tried is the temporal XOR, in which the system has to remember the step before and sum it to the current step. It's a task that requires a bit of nonlinearity and some short-term memory, and is a minimal task that you can do. These are the results that we obtained. So we show that by increasing the training size kind of fast, we reach a sort of stability. It improves the performance, of course, the less noise that you have on your reservoir. And experimentally, we did this by doing averages of the measurements. And we see that there is a good agreement between the experiment and the simulation. So we called this the digital twin of the experiment. Another thing that we did is the fading memory. So it has to remember the steps before that we encoded. And we saw that it's fading for sure. It now fades very fast. But we can improve it a bit, at least on the experiment, by sort of repeating the experiment slightly differently, which we call spatial multiplexing, as if we had different waveguides available. And once again, we have a good agreement between digital twin and the experiment. So yes, it fades very fast, good agreement, and it improves a bit with this spatial multiplexing. Then finally, we stopped using the experiment because we didn't have enough time. But we used the digital twin to see what would happen if we tried some forecasting task, meaning that now our reservoir has to learn the behavior of a chaotic series and predict the next step. So we took the data set that is called double scroll, which requires higher order nonlinearity and showcase this forecasting ability. So as you can see, the capacity goes quite high, even with noise. This is with experimental noise, with relatively small training sizes and a bit of multiplexing, yes. But you remember that there was the other possibility that we didn't do experimentally, but there is the possibility, is to do some pump spectral shaping. Meaning that now, instead of just rotating the whole pump, we're going to take our pump spectrum, divide it into sections, and put a different phase on each section, a different phase that will depend on the input, of course. So in this way, we will have some encoding modes and then some readout modes, so the one that you actually measure with your spectrally shaped local oscillator. This is actually very interesting because now, since we have some differentiation on the phase pump, on the whole pump, it will not be exactly Gaussian anymore because there will be different rotations on the spectrum. And in this way, every observable will be slightly different. This is what you see there. While when we were using the global phase, in the end, all observables were rotating the same. Nice, not nice carpet, nice carpet. Especially we see that actually if we increase the number of encoding modes, so we do a lot of sections of the pump, even just 5, we go to saturation of the expressivity. What does this mean? It means that every observable, every one of the n times n plus 1 over 2 is meaningful, is different from the other. And this means that we can reconstruct more complicated functions because we have more, let's say, ingredients to do so. This is nice, but let's try it on an actual task. So on the parity check task, which you just have to do again a sum, but a bit more back in time. And we see that not only it's better when you have more sections of the pump, but also fixing the number of sections of the pump. If you increase the number of encoding modes, now you actually gain in performance. And this is much better than the spatial multiplexing that we were doing before, because now you only have one waveguide. You're just a bit more smart. You're just a bit smarter about the encoding. Let's compare with other other approaches actually. So we went back to the double scroll, so the forecasting task in which you have to predict what happens next. And it was a bit difficult to compare with the other approaches because we have some modes that we measure, but then we actually have the covariance matrix. So there is this polynomial difference between what we actually use for the reservoir and what we actually measure. And also, yes, we have a lot of less parameters to tune because we're just doing a linear regression, while state-of-the-art processes for time series forecasting like LSTM have to do this very huge tuning, backpropagation, gradient descent thing. So we did two comparisons. The calculations are the same, just the plots are different. One in which we fix the amount of parameters to be trained, and one in which we fix the amount of neurons slash modes slash hidden units. Yes. So we are comparing with DESN, which is another type of reservoir computing but classical, in which we take a neural network and fix the first part, and LSTM, which are this state-of-the-art process, and another quantum protocol. So we see that if we take the same number of modes and neurons, we perform very well. We perform like LSTM, sometimes even a bit better, and much better than ESN because we have a lot more observables, so of course. This is the polynomial scaling. Oh no, sorry, I'm confusing. And then when you fix the amount of parameters, meaning that you train with the same number of things, we perform like the ESN and much better than LSTM because the LSTM has this very huge hunger of optimization. So just to conclude, we've showed a machine learning process that learns to do stuff with a minimal training cost. And more importantly, it's a machine learning process in which you don't need to touch the experimental platform during training. Like you literally do the whole training and just after do the linear regression on your data already taken, no need to touch anything. We did the experimental realization, showing that we have no linearity, we have fading memory and forecasting capabilities. We work at room temperature, the squeezing should be always there, modulo some aligning procedures. And we have an accurate modeling of experimental noise. We showed that we can actually exploit the pulsed light to do this general encoding, where we show that we have state-of-the-art performance and a polynomial advantage with respect to the other classical processes. And of course, we can still improve phase stability of the experiment, acquisition process, and do the general encoding experimentally. So I thank you for your attention. Here you have the QR code of the paper if you want. And thank you very much.
Okay, so questions.
I can start.
Yep.
Very cool result. Maybe I have I would like to ask some experimental details on, for example, how many modes and how much squeezing is required to perform the experiment. And also, maybe even before that, so you encode the input in the covariance matrix. Am I correct?
On the phase of the pump.
On the phase of the pump, okay.
Yes.
So I was wondering where the non-linearity comes from.
It's mostly from the measurement, actually, because since you have a projective measurement and you have your
I-
correlations, like the basis gives you a bit the nonlinearity.
Is the measurement back action on the system, or is the measurement on the data?
The
Alright.
measurement of the, like you
Okay.
have your squeezing ellipse that rotates, and since you
Okay.
have a projection, so at least you have cosinus and sinus.
And so what is the size of the reservoir, and how much squeezing do you need to do this?
So we had around 1 dB of squeezing, which is not a lot, so it's okay. The important thing is that the results are readable. Then we don't care about so much
Sure.
squeezing, yes.
And how many modes in general?
So on the experiment, we could, in general on these experiments, 20 modes have been measured. So this is doable. Yes.
Cool.
Any other? Oh, carry on.
Maybe a follow-up on this. How did you come to this number of 20 modes, or let's say in the amount of nonlinearity you need in the reservoir? Did you try different parameters, or do you have an intuition of what is the requirements?
So we had before the experiment and then the protocol, so we couldn't really choose. It's true that you can do the calculation of the number of modes that will be squeezed, and usually it's much higher than 20, but the resolution of the homodyne, the noise of the experiment, it's the limiting factor mostly.
Okay, thank you.
Also the power of the local oscillator, because if you divide into narrow bands, then you basically don't have power anymore to amplify.
Thanks.
Thank you.